video I'm going to be talking about implicit Runge-Kutta methods. Okay, so just to remind ourselves what the general form of an implicit Runge-Kutta method is, here we have the butcher tableau with our A values, our C values and our B values. So if we concentrate on the expression for the stage values Ki, okay, so K1, K2 up to Ks, these are all dependent upon our ODE function. So remember, our ODE function is f of ty, and instead of t we have tn plus some number c 8 times h, and instead of y we have yn, which is our current solution, plus a weighted sum of the other stage values. So notice here these will be implicit expressions. So for example, K1 is on the left here, and K1 will also appear on the right. Now if we consider the expression for K1 to start with, and I've expanded out the summation, excuse me. Okay, so what we're going to do is we're going to do some form of simplification. So I'm going to let big Yi be the second argument in f of ty. So it's all of this I've highlighted here. I'm going to say let big Yi be equal to that. So then our stage value for Ki is equal to our function Tm plus Cih, and we just have a single value Yi as the second argument. So if that's the case, what we can do is we can replace this Kj here in our expression for Yi with f of Tn Cjh Yj, because notice we're using j as the summation counter because I has already been used up there. So if we solve for each of our stage values, big Y, I, and then we update the solution using this. Okay, so that's some form of simplification of the implicit equations. Okay, so let's have a look at an example. This is from the lecture notes. So we're going to use a RAD-L1A method using a step length of 0.1 for this ODE here, initial value problem. I left this deliberately simple so we're not doing too difficult calculations, and it's a single equation, and the RAD-L1A method is here. If you look this up, this is the butcher tableau for the RAD-L1A method. So using our expression for Yi, so I'm just going to go back a slide, so I'm going to be using this one here. Now our f of ty in this case is t minus y. Okay, so we'll come on to that in a minute. So y1, okay, you can see our existing solution plus h, and then we got our summation of two terms, a11 times our function, with the second element being big Y1, and we have a12 times our function with the second argument being big Y2, and similar for Y2. So we know the values of our A values, and we know the values of our C values because they're from this butcher tableau here. So if I insert those values, and we have f of ty is t minus y. So this quarter here, that was a11. This 0 here, that was c1. And our function was t minus y. Well, instead of t, we got tn plus c1h. And instead of y, we have big Y1. A12 was minus a quarter. Okay, and C2 was 2/3. So instead of t in our function, we have tn plus c2h, and instead of y, we have big Y2. And that's similar for the second stage. Okay, so A21 was a quarter, A22 is 5/12, and we have the same function evaluation as we have in the previous stages. So what we now do is we have implicit equations. We've got y1 here and a y1 on the right, and we have a y2 here and we have a y2 on the right. So I'm going to rearrange these equations so that our big Y1 and big Y2 are all on the left hand side, and anything which we know the value for is going to be left on the right hand side. So we know what Yn is, we know what H is, and we know what Tn is. So everything on the right hand side here is already known to us. On the left hand side we know what H is, but we don't know the values of Y1 and Y2. And this can be simplified somewhat and written as a matrix equation. So here we have a linear system we have two equations and we have our two unknowns, and our unknowns are y1 and y2. So if we solve this matrix equation, we solve for y1 and y2, and then we can when we have our stage values. Okay, so our values for the first step, our initial value for t is 0, our initial value for y is 1, and we have h is 0.1, which if we plug that all into this equation, we get these values, and we can solve that using any linear system solver, for example LU factorization, to give us our values of y1 and y2. Now we have our stage values, we plug them as well as y0, t0, c1 and c2, and b1 and b2, into the Runge-Kutta method, plug the values in, perform the calculations, and we get our solution. So that's one step. So if I just go over what we've done. Okay, so we have our stage values. This gives us, in this particular case, because this is a linear ODE, it gives us a linear system of equations to solve. We solve those, and then we update our y value. Okay, well the problem is when we've got a nonlinear equation, when we have a nonlinear system of ODEs, we don't always have a linear system to solve for the stage values. So we have to use another approach, and the approach we use is an iterative approach, which uses Newton's method. Now you met Newton's method before in your second year. I just refresh your memory. So if we have a function g of x, so this blue line here is some function g of x, we want to know, well, for what value of x is g of x equal to 0. So that's the root of g of x. And so what Newton's method does, it starts with some guess value. So the superscript k in brackets is the kth guess value. Okay. We look at what's the value of our function g at xk, and we use the tangent of the function at that point, and we look at where the tangent intersects with the x-axis, and that's going to be our next guess for the root. So we do the same again. We look for where what the value of g is at that guess value. Okay, we look at the tangent, where the tangent intersects with the x-axis, that's our next guess value, and so on and so forth. If we keep doing those iterations, we'll eventually get to this point here. So this is Newton's method down here. So if xk is a current guess value for the root, xk plus 1 is the improved guess value, and g is the function for which we're trying to find the root of, and you notice this denominator here is the derivative of g. Now that's for a single equation. Now for a system of equations, this derivative is going to be what we call a Jacobian matrix. So if we have big N equations, so we got let's say we got big N number of functions, we've got g1, g2 up to gn, and we want to calculate for what values of x, x1, x2, etc., are all of these equal to 0. So we have a homogeneous system. So if we let x be the vector of x1, x2, etc., and g in bold, notice that's subtle, that's in bold. If that's a vector of our containing our functions, then we can write this system as a vector equation, and the vector form in Newton's method is this. So these are all vectors. This J here is known as a Jacobian matrix, and on the next slide I'll just show you what that is. So the Jacobian matrix, so remember we have a vector of g1, g2 up to gn. Well, the Jacobian matrix, each row is each function but differentiated with respect to one of those variables, so x1, etc., x2, and going across. So each row contains a different function. g1 is on the first row, g2 will be on the second row, etc. Each column is differentiated with respect to a different variable, x1, x2, etc. Now the problem with calculating an inverse Jacobian matrix is computationally expensive. If you've got a 100 by 100 system of ODEs, you're going to have to calculate 100 by 100 inverse, which is very computationally expensive. So what we can do is, if we let delta x be the difference between two successive estimates of x, then we could rewrite this. So if I subtract xk from both sides and pre-multiply both sides by j, So multiply j inverse by j, we just get the identity, so it's essentially 1. We get this equation. Now this is a linear system, because j is just going to be a n by n matrix. We have a vector of unknowns, delta x, equals some right hand side, which is our function g. So that's a linear system, and we simply solve that linear system for delta x. Then we update our estimate using this equation here, which is just a rearrangement of that original equation. Okay, so using Newton's method, we actually solve, we calculate the Jacobian, we solve a linear system, and that gives us our improved estimate. So each iteration in Newton's method, we have to solve that linear system. Okay, so we're going to be using Newton's method shortly to calculate or to apply an implicit Runge-Kutta method. But before I do so, I just need to introduce an idea called the tensor product, also known as Cronetta tensor product. And quite simply, if we have two matrices A and B, the tensor product is denoted by this what we call an O times symbol. So it's a time symbol in an O in a circle. Okay, so for example, I've got two 2x2 matrices here with elements A's and B's. The tensor product is essentially one matrix is multiplied by each element in the other matrix. So if I take the second matrix with the B values, you can see each matrix is multiplied by one element in the first matrix. So the second matrix is multiplied by each element in the second matrix. So this gives us a 4x4. So we've got two 2x2s, so we have a 4x4 in the end. So that's a tensor product. Now the reason why I'm introducing this is because we're solving for a system of ODEs, and each ODE is going to have a number of stage values. We're going to have quite a lot of combinations of elements to think about. Okay, so now if we move on to looking at solving systems of ODEs using implicit Runge-Kutta methods. So if we're presented with a system of ODEs, okay, so y is a vector, f is a vector of functions, and that's the functions are arguments are the t value, which is independent variable, and the vector y. Okay, so you can see the vectors y and f of ty defined here, and this is the vector form of an IRK method. Now, as before, we're letting big yi be equal to this, equal to the second argument in our stage value calculation. So exactly the same as what we did before with the one equation system. We end up with this. Now, writing each stage value out for I equals 1 to s, that's all our stage values, we'll have a vector of vectors. So each of these elements yn is itself a vector. And likewise in this matrix here, we have a summation. Okay, so this is a summation across the first row of A multiplied by f, which is itself a vector. So this is where the tensor product comes in. So we have vector of vectors, so we can use the tensor product to simplify our equations. So for example, each summation here, so I'm going to take the y1 example, so this summation here, that is itself a vector. So for that summation we have this vector here, and all of these summations within the vector can be written using an n by n identity matrix. So these summations here, okay, so we've got so if we take the first one, we've got a1j multiplied by an n by n identity matrix, multiply it by a vector of functions. So we can simplify that to be a1j times the identity matrix times our vector f. Now that's just for the first, if I go back a slide, that's just for the first one. So for each of the ones we have the same expression. So for all s stages, okay, so we can write it like so. Okay, so we have this matrix multiplication. This replaces the summation within the stage expression for the stage in the run cutter method. Okay, so and this equation here, this bracket here, this is equivalent to our matrix A tensor product with the identity matrix I. Okay, so this whole thing here, that can be simplified to that one there. We can introduce vector notation as well. So I'm going to let big Y be our vector of stage values. Okay, so that's also going to be a vector of vectors. Big F is going to be our vector of our functions. Now remember, each of these little f's is itself a vector. And I'm going to let E be just a vector of ones. Okay, so that means we can rewrite our stage value calculation as this. Okay, so this is our vector of stage values, and remember each stage values has multiple or S number of elements. So we have the tensor product between E and Yn, well that gives us this vector here, plus H times the tensor product between A and In, so that's that there, and multiplied by big F. So you can see each one of these, so big F was this vector here. Okay, so that's our stage values for an implicit run cutter written using tensor products. And we could also use tensor products to write our updated value for Yn+1. So we have B transpose, and remember we always use B, the vector B is always a column vector, so B transpose is a row vector. That's tensor product with the identity matrix multiplied by that same function big F. So what we do is we solve for big Y using Newton's method, and then we update our solution, our vector of Y values, using this expression here. So to calculate stage values, we need to apply Newton's method, which we looked at a few slides ago. Now, so we need that function g, which is the function we're trying to find the root of. So going back to our stage value calculation, if I subtract y from both sides here, we have our function g of y. So we want to find for what values of big Y is g of y equals 0. Now the Jacobian matrix of this, if we were to differentiate this with respect to each of our big Y terms, we get this. So INS, so N, big N, is the number of equations in your system, S is the number of stages in your method. So we'll have an N times S by N times S identity matrix. Okay, and that's equal to this here. This big Y is, big F is differentiated with respect to big Y. And remember, big Y had Y1, Y2, Y3, etc. So this is the Jacobian matrix. Okay, so Jacobian matrix is this. Okay, so if you can see here, each element in this Jacobian matrix has a Jacobian matrix itself. Okay, so bold F differentiated with respect to Y, this is going to be an S by S Jacobian matrix. Okay, so we need to use tensor products again, because we have a matrix of we have this JY here, this is going to be a matrix of matrices, because each of these is itself a Jacobian matrix of our original ODE system. So this is what I mean by that here. So these terms are all n by n Jacobian matrices for the system of ODEs being solved. Now the problem is calculating those Jacobian matrices at every iteration can be very expensive. So we tend to use a bit of a fudge, we tend to use a simplification, and we're simplifying our f of our big F differentiated with respect to big Y, so that's this term here. Okay, we're simplifying that to use the S by S identity matrix tensor products with our original ODE system with respect to the variable Y. Okay, so that might be y1, y2, y3, or little y1, little y2, little y3, etc. So this is it is a simplification, but remember we're using Newton's method, which is itself an approximation for our big Y values, so that's fine. So our Jacobian for our Newton's method simplifies to this. Okay, so that's much more easier to calculate than all of this. Sometimes it's not possible to calculate this Jacobian here, so we just use finite difference approximations for each derivative. Okay, so this is a first order finite difference approximation, and that replaces that term there. Sometimes you can calculate the Jacobian, sometimes you can't, depends on the problem. Some sophisticated ODE solvers will also give you control of how often you recalculate the Jacobian and things like that. So once you've calculated the Jacobian, we can use Newton's method, and the matrix form of Newton's method is here. So remember, this is a linear system. Okay, so you have your Jacobian matrix. Delta y is what we're solving for, and we know what minus g y of the current Kth estimate of big Y is. So this is a linear system which we solve, and then we update our estimates for big Y. Okay, we need some starting values for big Y, so we tend to use the vector of ones, which is E, tensor product with our current solution yn, and we continue to iterate until the norm of our delta y vector is less than some small number, the tolerance. So here's the algorithm. Okay, so if you were to code this up, this is the algorithm you'd use. So if you're presented with a system of n first order ODEs, okay, of the form y dash equals f of ty, we have some domain t min to t max, and we know our initial vector of solutions at t min and a step length h and an accuracy tolerance tol. So as usual, we initialize our initial solution y0, our initial value for t0, and we set our counter, so this is the number of steps we're doing, we initialize that to 0. And we define our whatever Runge-Kutta method we're using, our A, B and C arrays, as well as a number of stages S. So we loop through the domain, we initialize our guess values of big Y to be a vector of ones tensor product with the our current solution little yn. We pre-calculate this Jacobian. Okay, so we're assuming the Jacobian is not going to change relative to big Y. In essence it does, but we're prepared to sacrifice some efficiency in the Newton's method for ease of use. So we calculate this. Notice sometimes this Jacobian here might need to be approximated using finite differences. Initialize an error to be some number which is bigger than tol, so for example 1. And while that error is bigger than tol, we calculate our gy function. So this is a straightforward calculation in terms of most programming languages have some form of a command for the tensor product. So in MATLAB that's cron, so kron is the command for tensor product. So this is a straightforward calculation. We then solve the linear system for delta y, so that might be using LU factorization or some other method to solve a linear system. Once you've got delta y, we update our guess value for big Y, and we calculate the error, which is the norm of our delta y's. And we keep doing this until we have our norm, or the change in big Y, is less than some tolerance, and we quit. So that normally takes around, it should take less than 10 iterations. If it takes more than that, there's probably something's gone wrong somewhere. So after doing Newton's method, we have our values of big Y, and we update our solution using our Runge-Kutta method here. Okay, this algorithm I presented here is not hasn't included any adaptive step size control. Some sophisticated solvers do include that. Right, so let's have a look at an example. I'm going to look at a simplified example of just two equations. Okay, so two ODEs here, and our two variables are y1 and y2, and we have our initial values for y1 and y2, so 0 and 1. And I'm going to use the radl1a method, same as the one we used previously. Okay, so in this case, because we got it's possible to differentiate this system. So if we calculate the Jacobian, okay, so the first equation, if we differentiate that with respect to y1, we get 2, and if we differentiate that with respect to y2, we get 1. And for the second equation, if we differentiate it with respect to y1, we get y2, and if we differentiate it with respect to y2, we get y1. So in this case, it is possible to calculate the Jacobian. So we need to calculate that big JY, so that's this one here. Okay. So if we evaluate the Jacobian matrix, now we have two equations in our system, but we're going to have an an n times s by n times s. So we've got two equations in the system, two stages in our method, so we're going to have a 4x4 identity matrix. This matrix here, okay, if I look at the first 2x2 terms, okay, this is our A11 tensor product with I2. Okay, and if we move across to the next 2x2 sort of block, this is our value of A12, which was minus a quarter tensor product with I2. So you can see that's where that 4x4 matrix comes from. And similar with this one, so this is our 2x2 identity matrix tensor product with this matrix here. Okay. Do the calculations and we get this 4x4 matrix here. We know what h, y1 and y2 are, so we can actually calculate our value for j, big Y. Okay, so for the first step, y1 is 1, y2 is 0, and we've chosen a step length of 0.1. So if we do the calculations, this is our Jacobian matrix. If we're using Newton's method, we've got to initialize y0. So remember, y0 is just the tensor product of 1 by 1 vector with our initial values of y1 and y2, which gives us that. Okay, and therefore our big F is equal to, so this is each of these applied to our ODE function. Okay, so if I just go back, so the first ODE function is 2y1 plus y2, so that's y1, that's y2. So y1 is 1, y2 is 0, so 2 times 1 is 2, plus 0 is 2, and the second equation was y1 times y2, so that's 1 times 0, so that's 0 there, and it's repeated below. So we've got our initial value for big Y, we've got our initial value for big F. Okay, so then calculate g of y for our first estimate. So we have y0, we have e tensor product with y0, okay, minus h, which is 0.1, a tensor product with I2, which is this, multiplied by our big F, okay, and that gives us this vector. So this is an n times s, so number of equations in our system times the number of stages in our method by 1. Okay. Now we need to solve the linear system jy, our Jacobian multiplied by delta y is equal to minus g. So this is our g, okay, and our Jacobian was this. Okay, so if we solve that using whatever linear solver you're going to use, we have delta y is equal to this. Now this is our change in our in our big Y. So if we add it to our current estimate, we get our new estimate of big Y. And if we calculate the norm of delta y, we get 0.1452. So that's bigger. That's quite a big number. So we need to iterate our Newton's method again. So doing it again actually results in very small values for delta y. So less than 10 to the minus 13. So our next value of delta y is very, very similar to these values here. So it's converged after just 2 iterations. So our values for big Y are these. So we're fairly certain, or we are very certain, that these are our values for big Y. Okay, so if we plug those into our updated solution for our implicit Runge-Kutta method. So this 2x4 matrix here, this is B transpose, which remember is a 1x2 matrix, tensor product with a 2x2 identity matrix. That's what we get here. Okay, so this is the B1 multiplied by I2, and this is B2 multiplied by I2. Okay, perform these calculations and we get our solution for Y1. So this is our solution over one step of 0.1 for that problem. So for all other steps we have to do the same thing. So for all other steps we recalculate the Jacobian because our Y1 and Y2 will have changed. So we have to recalculate the Jacobian. We have to perform Newton's iterations again to calculate big Y. And once Newton's iterations are converged, we then plug those values into our Runge-Kutta formula here, and that will give us our next step. So it is a quite involved, using an implicit Runge-Kutta method, it is a quite involved set of calculations, but as we saw when we looked at stability, they have much better stability properties than explicit methods.